These notes are over gravity. So there's 4 fundamental forces that govern the universe. And these are strong nuclear forces, which is an attractive force that holds together nuclei. There's electromagnetic forces, so this can be both an attractive or repulsive force that, like with charges, like charges, they're going to repel each other compared to charges that are opposite, they're going to attract each other. There's weak nuclear force, and then there's gravitational force. Okay, so gravitational force of these 4 is the weakest, but it's actually very long ranged. So it's also always an attractive force. Okay. An important thing to note too with gravitational force is that it is a force that is experienced between 2 objects without them touching. Okay, so that's why it can be long range. The distance doesn't matter. The gravitational force can still act upon 2 objects. Okay, so these 4 fundamental forces determine the structure of the universe. Okay, but because we're talking about Newton's mechanics, we're going to focus on gravitational force. Okay, so like I said, gravity is an attractive force, and it is at a distance force. Okay, so they do not need to be touching. The closer 2 objects are, the greater the gravitational pull, but you can still have gravity affecting 2 objects that are far apart as well. Okay, so an interesting fact is that our sun and planets, they all were kind of formed because the cosmic dust after the Big Bang came together due to gravity to create these different objects, such as the sun, the earth, the different planets. Okay, and so just kind of as a tangent, if you know anything about space and the creation of space, in the explanation through physics, is that the universe is expanding, okay, and that's just due to the amount of energy that was produced in the Big Bang, okay, but what they theorize is that eventually the gravitational pull will overcome that force, and that the universe will start sinking back in on itself due to gravity. Right? So just kind of an interesting thought. But if you and a beloved of yours were the only 2 things left in the universe, and you were billions of kilometers apart, what would happen is that eventually the gravitational force between you 2, even though you're very, very far apart, eventually you guys would come together and meet. It would just take a very, very long time. So that's very similar to what I was just explaining with the different cosmos. Okay, so on Earth, we know that acceleration due to gravity is 9.8 meters per second down. Okay, so using Newton's second law, we can see that the force of gravity is meters or mass times gravity. Okay, so gravity of the object, because we substitute the acceleration for gravity. Okay, so it's the same equation, except that gravity is a constant in terms of here on Earth. Okay, so one thing to note is that the force of gravity is different than the acceleration of gravity. Okay, so the acceleration of gravity is a constant here on Earth, okay, at 9.8 meters per second down. And it does vary slightly depending on how far from Earth's center the object is, but for the most part, it is a constant here on Earth. Okay, the force of gravity is going to be different depending on the object. So an object that has a greater mass is going to have a greater experience a greater force due to gravity compared to a smaller mass object. Okay, so the force of gravity is generally called the object's weight. So in physics, we distinguish mass, which is the amount of matter an object has, measured in kilograms, with weight, which is the force that is experienced by the object, and it's measured in newtons or in pounds, and it can be converted back and forth. Okay, so if we're to travel to different planets, one with different acceleration due to gravity, our mass would stay the same because we are still made up of the same amount of matter, but our weight would change because the gravitational force or gravitational acceleration, thus the force we feel, would be different depending on that planet. Okay. So moving on for an example, a 500-gram apple falls experiencing gravity and then falls towards the earth. Determine the force of gravity acting on the object. So we're going to use the force of gravity equals mass times gravity. Okay. Our mass is 0.15 kilograms because we need to convert this to kilograms in order to get the newtons that we need for force. Okay. Our gravitational acceleration is 9.8 meters per second squared in the downward direction. Right. So whenever we plug this in, we get negative 1.47 newtons. So the force of gravity on the apple is 1.5 newtons down. So when an object is in free fall, it doesn't necessarily accelerate towards the ground the entire trip. Okay, especially here on Earth, it's going to experience air resistance. And once the air resistance is large enough, the downward force of gravity is going to be balanced by that air resistance. Okay, so when this happens, the object no longer accelerates toward the ground. Instead, it moves at a constant velocity, which is known as terminal velocity. So a lot of times we hear the term terminal velocity with like skydivers. So the terminal velocity of an object depends on many factors. This includes the mass of the object and then also the surface area of that object. Okay, so we've experienced this. Objects such as like a bowling ball falling compared to a flat piece of paper, we see that they kind of accelerate towards Earth at different speeds, and that is due to the air resistance pushing upward. Okay, if they're falling long enough, they all experience that balance of these two forces. If we have a skydiver who is 65 kilograms, and they jump out of the plane and experience 115 newtons of air resistance. If we to draw that, we have our person who's 65 kilograms. We have our air resistance, which is going to be pushing up on the object or the person at 150 newtons. Okay, and then they're experiencing gravity in the downward direction. So the force of gravity equals mass times gravity. So the mass was 65. Gravity here on Earth is 9.8. So the gravitational force that this person is experiencing is 637 newtons. So if they were to achieve terminal velocity, that means that the air resistance is going to equal the gravitational force that the person feels. So if the person is experiencing 637 newtons down from gravity, they're going to feel 637 newtons up if they've reached that terminal velocity. So they're balanced, okay? And so when we have these balancing arrows, okay, or vectors, we know that we can add the vectors together and we would get 0. Okay, and that 0 is just indicating that there's no more acceleration. It's not saying that the object has stopped, it's just saying that there's no more acceleration, and so they are now going at a constant speed. I want to talk about this problem, question 5, instead of assigning it, just because it's kind of a confusing question. So here it says that in 2012, Felix Baumgartner, an Australian skydiver, ascended into the stratosphere using a helium balloon. He jumped from a height of 39 kilometers above Earth's surface. Okay, so do you think that 9.8 meters per second can be used to determine his acceleration as he jumped out of the capsule? Why or why not? Okay, so the 9.8 meters per second is the value near Earth's surface, and so 39 kilometers is actually too high up to use the 9.8, okay? But we never really kind of established what is too far from Earth's surface in order to change that constant of 9.8. And so actually on the top of some of the taller peaks of mountains here on Earth, there is a slight difference in the pull of gravity at that point, okay? So I kind of just wanted to touch on that. For part B, draw the FBD for Baumgartner before he pulls his parachute. Okay, so before he pulls his parachute, it should be that he has reached terminal velocity. Okay, because he's definitely going to experience terminal velocity before he would reach Earth's surface. Okay, so we have equal values for our force on the air and then force of gravity. And then for part C, Baumgartner's maximum speed was 1,357.64 kilometers per hour. Draw the FBD for Baumgartner after he pulls open the parachute. Okay, so after he pulls open the parachute, the force of air resistance is actually going to be greater than the force of gravity. Okay, and so because of this, it's going to decelerate him towards the downward direction. So it's going to accelerate him in the upward direction, which is going to decelerate him from the downwards direction, which helps to create a safer landing.